All right, second practice problem, started with sample problem A here in chapter 4. So number 2, a physics book is at rest on a desk. Okay, so I'm going to go ahead and draw a physics book. How should I draw it? What's the best way to do it? Should I go fancy? Should I go fancy? That, and then that goes like that, and then we got the actual pages, and then that's what we have here. Let's see, and that's gonna go back here. That other border. Okay, perfect. Oh my gosh, look at that. Oh. All right, get a little Latin in there. Okay, don't fact check me on that one, but I'm pretty sure that's Latin. So here is our physics book. It's on a desk, but we're not going to do this because we're drawing a free body diagram here. We're only going to represent the object, and then we're going to represent the forces that are acting on the object or by the object using vector arrows. Okay, so it's not like we're going to draw the desk. So, and that's how you differentiate between a force diagram and a free body diagram. Okay, free body diagram, free body, body in free space. We're just talking about the one body, that's it. Gravitational force pulls the book down, obviously. So let's draw our point at center of mass. Go down. It is the force due to gravity. Okay, we good? Now, the desk exerts an upward force on the book that is equal in magnitude to the gravitational force. And that would make sense. But I'm going to represent that with a vector arrow that has the same length as my force due to gravity. Okay, we'll call that. What we're going to find is this actually ends up being the normal force. You don't have to know it's normal force quite yet, but that's where we're moving to. So this is going to be the force that's exerted on the book by the desk. Okay. Now, if we look at this graphically, again, we have to represent that because the physics book is at rest. Okay, it's not moving. Okay, acceleration is 0. That the net force on the book is 0. It means whatever force of gravity is being exerted on the book, it's being completely balanced out by the force exerted on the book by the desk. So, how do we represent that mathematically? Well, if we were to take the force of gravity, which we could represent as being a negative value, right? Because the direction is in fact down, and we add that to the force that's actually holding the book up, that would actually add up to 0. Okay, and when there's no net force on an object, there's no acceleration. That means there's no change in motion. There's no change in motion. That's why the physics book is in fact at rest. If these forces were not completely equal in magnitude and opposite direction, like if they weren't in the exact opposite direction or they weren't equal in magnitude, you would actually generate a value here. The sum of the forces wouldn't be 0, there'd be some value, and you would have acceleration. And you'd see that kind of on the macro level as seeing this physics book move. It would have some sort of change in motion.